In the vast, cold clouds of gas and dust that drift between the stars, gravity is a patient sculptor. Over millions of years, it pulls these clouds into tighter, denser clumps. As the pressure builds, the core begins to glow with heat. If it gathers enough mass, it crosses a critical threshold, and a star is born. Look to our own solar system for a near miss. Jupiter, a colossal ball of gas, is a failed star. It is immense, but it never grew massive enough to ignite the fires of nuclear fusion. It remains a gas giant, a king of planets, but a star it is not. The secret to a star's life is turning matter into energy. In its core, the crushing pressure fuses hydrogen atoms into helium, releasing a torrent of light and heat. This outward push of energy is what holds a star up, fighting a constant, desperate battle against the inward pull of its own gravity. For billions of years, this celestial balancing act defines a star's existence. While our sun is a respectable size, the universe is home to giants that defy imagination. Consider Stephenson 218, one of the largest stars we've ever found. It is a red hypergiant so colossal that if you placed it at the center of our solar system, its edge would stretch out beyond the orbit of Saturn. Our Earth would be nothing but a speck of dust deep within its fiery atmosphere. These are the titans of the cosmos. Their immense mass means their gravity is far stronger, and to fight it, they must burn through their fuel at a furious, unsustainable rate. While our sun will live for 10 billion years, these giants live fast and die young, burning through their entire fuel supply in just a few million years. And their deaths are the most violent events in the universe. To understand how a star dies, we can look to our own night sky. Find the constellation of Orion, and you'll see a brilliant, reddish star marking his shoulder. This is Betelgeuse, a red supergiant and one of the most famous stars in the sky, for one simple reason: it is a time bomb. Betelgeuse has exhausted the hydrogen in its core and has swelled into a colossal, unstable giant. It is in the final stages of its life. Astronomically speaking, it is expected to explode soon, which could mean tomorrow, or it could mean 100,000 years from now. But when it does, it will go supernova. Located about 640 light-years away, Betelgeuse is too far to harm us, but the show will be spectacular. The explosion will blaze with the light of 100 billion stars, outshining everything in the night sky except the moon. It will be so bright. It will be visible during the daytime for weeks. It will be a constant, beautiful reminder of the cosmic violence that unfolds across the galaxy. For a massive star, death begins when it runs out of fuel. With the outward push of fusion gone, gravity wins the battle. In less than a second, the star's core collapses catastrophically, crushing itself down to an object of unimaginable density. This collapse triggers a rebound, a shock wave that blasts outward through the star's outer layers. This is the supernova. The explosion releases a quantity of energy that is almost impossible to comprehend. In a matter of seconds, a single supernova will release more energy than our sun will produce in its entire 10 billion-year lifetime. For a brief period, a single dying star can outshine its entire home galaxy. What if our sun were to go supernova? Thankfully, it's far too small for such a fate. But if it did, the Earth wouldn't just be burned. It would be utterly vaporized in an instant. The blast would sterilize our entire solar system. This is the power we are dealing with. And yet, there is another level of destruction. For the truly massive stars, those more than 30 times the mass of our sun, a simple supernova is not enough. Their death is a far more violent and exotic event. A hypernova. A hypernova is a supernova on steroids, potentially 100 times more energetic. The collapse of the core is so extreme that it doesn't just trigger a shockwave. It forms a spinning black hole that drills its way out from the inside. This process launches twin jets of matter and energy that scream into space at nearly the speed of light. If one of these jets, a gamma-ray burst, were aimed at Earth from a nearby star, it would be a true extinction-level event, capable of stripping away our ozone layer and wiping out life on the surface. After the fire and fury of the explosion fades, what is left behind? The supernova leaves behind a cosmic ghost. In the center of the expanding cloud of gas, all that remains of the star's core is a neutron star. This is one of the strangest objects in the universe, an object the size of a city, yet with more mass than our Sun. It is so dense that a single teaspoon of its material would weigh 1 billion tons. But if the star was massive enough to go hypernova, the core collapses completely, and nothing can stop it. Gravity wins its ultimate victory, and a black hole is born, an object so dense with gravity so powerful that not even light can escape. These spectacular deaths are not just endings. The elements forged in the hearts of these stars and blasted across the galaxy, the carbon, the oxygen, the iron, are the very building blocks of new stars, new planets, and even ourselves. The death of a star is a necessary sacrifice, a violent, beautiful act of cosmic creation.